There's the last day. There's a lot to do. We're going to talk about the different perspective on the hardness of boson sampling. We're going to talk about approximate boson sampling, which is actually sort of the subject of our main technical results. The exact case is sort of the the easy one, but also not really the physically, most realistic one, you could say. And then I'll talk about quote-unquote experimental issues. So how do you scale? How do you do a boson sampling experiment? What's the point? What are you trying to do with one? Could you actually scale it up to a computationally interesting number of photons? How would you do that? And supposing that you did do it, how would you verify the results? All right, so I'm going to try to touch on all of that. So just to recap what we did last time. So last time I explained this argument that we gave why the exact boson sampling problem is probably hard for a classical computer. Okay, namely, if you had a fast classical algorithm for it, then that would collapse the polynomial hierarchy. Okay, and this argument is actually a very, very straightforward one, right, by complexity standards, but it has various aspects that like one that may be sort of hard to wrap one's head around. Okay, and in particular, what's crucial to understand is that nowhere here are we arguing that boson sampling itself is a sharp p-complete problem. Okay, that is not what we're saying. And in fact, I went to some lengths yesterday to explain why, we don't think that a boson sampling device would let you actually calculate the permanent of a matrix of your choice, in a, better than a classical computer could do it. Or at the very least, we have no idea how to do that. Okay, and I explained why that was, because, you'd have to embed your matrix into a unitary matrix in order to do the experiment, but then you have to repeat exponentially many times before you see the particular outcome that tells you about the permanent that you want. Okay, but even though this is sort of the core of the of the entire argument. Okay, even though the boson sampling device does not itself solve a sharp p-complete problem, it does involve these amplitudes that are sharp p-complete, because they're permanents, and we can use that indirectly to argue that the sampling problem, the boson sampling problem, is most likely also hard. Not sharp p hard, but still hard. Okay, and what we do is we say, suppose imagine that you had a fast classical algorithm for the problem. Okay, then we're going to crucially use the assumption that we had a classical algorithm for the problem. Okay, and we're going to say in BPP with an oracle for NP, with an oracle for the classical algorithm for boson sampling, then we could do sharp p. Okay? That's what we're saying. So it's not that the quantum device itself lets you do sharp p. It's not even that a classical simulation of the device would let you do sharp p, but a classical simulation of the device would let you do sharp p in BPP to the NP. Okay? And the point is that would already be really bad. Okay, if that could happen. And the reason, and in some sense, it just says these two really high up complexity classes, both of which are sort of infeasible in the real world, would collapse with each other. Okay, so you might say, who cares, right? But this would be enough to have sort of disastrous consequences, for the complexity hierarchy. What it would mean essentially is that by estimating a sum of non-negative terms, which is already a sort of a hard problem in general, but which you can do in BPP to the NP, that would be enough to estimate a sum of both positive and negative terms, which is what you can do in P to the sharp P. Okay, so those two hard problems, those would become equivalent to each other, whereas our current picture of complexity theory requires this problem to be much, much harder than this one. Okay, if they collapse to each other, then the polynomial hierarchy collapses also. Okay, and the point is we can use our beliefs about what happens high up in the hierarchy to draw real conclusions about the hardness of simulating this actual real experiment with real computers. Okay, so we connect our belief about one to our beliefs about the other. Question? No? Okay, okay, good. So, all right, so now an interesting point here is that the argument easily extends to say, even if you had a fast classical algorithm for boson sampling that used, let's say, an oracle for NP-complete problems. All right, so I'll throw that in. I'll let you solve NP-complete problems for free. Or I'll even let you solve NP to the NP problems in the second level of the polynomial hierarchy. In fact, I'll let you do any level of the polynomial hierarchy that you want. Okay, so your randomized algorithm can access whatever level of pH it wants. Still, that would, if such a simulation existed for boson sampling, that would imply a collapse of the polynomial hierarchy. Okay, because that would mean that p to the sharp p would be contained in BPP to the polynomial hierarchy, which is in the polynomial hierarchy. Yeah.
I mean, you just every time you ask the oracle for something in the polynomial hierarchy,
Mm-hmm.
you not necessarily have any explicit bound on what do you ask, like which.
Oh, right, on which level? Yeah. So you do have to sort of this is sort of a standard issue in complexity theory, but you do have to fix a level, or else you have to say that querying at the kth level requires like n to the k effort, something like that. Okay. All right. Let's just say fix the level. Okay. For any fixed level, if you can do it in that level, then that's enough to collapse the hierarchy. Okay. Good. Okay. So today, what I want to start out with is actually a totally different argument that leads to the same conclusion, that exact boson sampling is classically hard unless the polynomial hierarchy collapses. Okay. Now this argument actually comes out of independent work from ours by Bremner, Joza, and Shepard. Okay, so independently of me and Alex Arkhipov, they gave sort of a beautiful alternative argument, which they were actually interested in a different weak quantum computing model than we were. We were interested in linear optics. They were interested in something that they called instantaneous quantum computing, or IQP. It's not really instantaneous, okay? That's just what they called it, okay? But it's a different sort of weak quantum computing model where basically all you can do is a round of Hadamard gates and then some classical computation and then another round of Hadamard gates. And then you can measure and see what you got. Okay, and so completely analogously to our result in the at least in the exact case. They didn't consider the approximate case. Okay, but in the exact case, they said, look, if you had an algorithm that's a fast classical algorithm that's sampled from the same probability distribution that our device could sample from, then the polynomial hierarchy would collapse. Okay, so actually, the much more important than the different model that they were considering is that they used a different style of argument than we did. And in fact, their style of argument can be ported over to linear optics. Our style of argument can be ported over to their IQP model. Okay, so it's all kind of interchangeable. So let me show you how their argument works in the setting of linear optics. Okay, after you port it over there, and then I'll show you like an interesting insight that this alternative argument gives you about the complexity of the permanent itself. Okay, so what they do is that they use a concept of post-selection. Okay, and this is something actually that many physicists are familiar with. So I don't know if I have to belabor it too much. This is the dirty secret of many a quantum information experiment. Right. Post-selection just means that you make some measurement and then you throw out all the runs of your experiment or of your computation where that measurement did not produce some desired outcome. Okay, so it means conditioning. Okay, so you can easily define complexity classes based on this concept of post-selection, and you can define complexity classes based on just about anything. So in particular, there's a class that I call post-BPP. Okay, and this is just this class of all the decision problems or languages that are solvable by a probabilistic polynomial time Turing machine. So it's like BPP. But now I'll give you an additional power, which is the power to post-select. Okay, you can say, the machine is going to produce some certain output bits, and we're going to just ignore the computation unless these bits are all set to 1. Okay, unless these flag bits are all set to 1. And crucially, it may only happen an exponentially small fraction of the time that all these flag bits are set to 1. Okay, but that's okay. We're still allowed to post-select on that happening, as long as it happens with some non-zero probability. Okay, so that's post-BPP. We can then ask, where does it fit in with, the more familiar complexity classes? All right, well, it's pretty obvious that post-BPP certainly contains NP. Okay, why? Because, if you have an NP-complete problem, just guess a random solution and then post-select on it being a good one. Okay, it's kind of like when people have these arguments about the many worlds interpretation. If you believe it, does it mean that you could solve NP-complete problems by, guessing a random answer and then you just shoot yourself if it's not the correct one? Okay, and then, in all of those Everett branches where you exist, then you have the solution. Okay, that's post-BPP. Okay, but, it's also easy, it can also be shown that post-BPP really, doesn't let you do much more than solve NP-complete problems. Okay, so we can get an upper bound that post-BPP can be simulated by a BPP machine, an ordinary probabilistic machine with an NP oracle. Okay, and the way you do that is using the same approximate counting method from classical complexity theory that I discussed yesterday, although I didn't explain the details of it.
So
yeah.
If you were to try to define post-P, is that just the same as a non-deterministic Turing machine?
Well, post-P, I think would just be, to the extent it makes sense, would just be equal to P, in fact, because if you don't get to make any random decision at all, then there's nothing to post-select on. You see what I'm saying? Right, so it really only makes sense if you have some source of randomness to begin with.
With a non-deterministic Turing machine, it's kind of the same, because you just look for
the
answers
well,
and take the one.
That's exactly what we're saying here. Yep. I mean, it could be a little bit bigger than NP because this one lets you do co-NP. I mean, it also at the least lets you do BPP, which we don't know how to do in NP, right? So it may let you do a little bit more, but this theorem says it's not too much more. So yes, the theorems agree with your intuition. Yeah. Was there another question? Okay. All right. But now things get more interesting when you consider post-BQP. Okay, which is just the set of problems that you could solve in quantum polynomial time, but with post-selected measurements. So now you get to measure some qubits and just assume that you're going to get the result 1. Let's say, okay, and so I had investigated this like a decade ago, for separate reasons, and at that time I proved kind of a surprising fact, which is that post-BQP is exactly equal to the classical complexity class PP, which I discussed before. Right? PP is like this decision class, right? It's like BPP, but with no gap. Okay, PP basically has the full power of sharp P, right? In the sense that P with a PP oracle already lets you do sharp P. Okay, so what this is saying is that actually when you combine quantum with post-selection, you get something that seems much, much more powerful than either one alone. Namely, you get the power to solve counting problems. Okay? And furthermore, that's exactly how much power you get. You don't get more than that. Yeah?
So is it clear that post-BQP is gate set independent?
That's something that has to be checked, but one can check that. That's true. And it follows because with the Solovay-Kitaev theorem, you can make the error be exponentially small, and you can make it be smaller than whatever exponential is involved in your post-selection.
So you're never exploiting non-zeroness of doubly exponentially small?
No, it's nothing like that. No. Yeah. 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 Oh, that is an excellent question. So let's see. I'm not sure if it would, if P equals BPP itself would give you this, but under the same sort of de-randomization hypotheses that led people to believe that P equals BPP in the first place, you would also get that post BPP equals, I think, P with a bunch of parallel queries to an NP oracle. Okay, so non-adaptive queries to an NP oracle. Okay, very good question. Yeah. Okay, so all right. So in fact, what was surprising here is that this quantum complexity class post BQP is exactly equal to a classical complexity class, PP. And in fact, I showed that one can use this to give, simpler proofs of some of the important, just purely classical theorems about PP. So there was a famous theorem that says that for any two languages that are in PP, their intersection is also in PP. Okay, why did people care? I'm not sure exactly, but it was a problem that took 20 years to solve, and then you use these sort of low degree rational functions. Very nice proof. Not that hard ultimately, but it's a non-trivial proof. What I found is that once you know that PP equals post-selected quantum polynomial time, then you can prove the same theorem in half a page. Because this post-BQP class trivially has this closure under intersection property. So then it's equal to this, then this one does too. Okay, so but in any case, what Bremner, Joseph, and Shepard realized is that we can also use this post-BQP, equals PP thing to argue about, the hardness of sampling problems. Okay, and how do you do that? Well, all right, the first thing, that I should tell you is that, we're of course interested in linear optics, right? Linear optics may be weaker than full quantum computation, okay, as we discussed. Okay, but I also told you yesterday about this KLM theorem, this discovery of Knill, Laflamme, and Milburn, that says that if you have linear optics and you just add one additional resource to it, which is adaptive measurements, then you get a universal quantum computer, okay? So sort of that's all you need to boost it up. Now it turns out that actually in the same paper of KLM where they do that, there's actually a much easier result, a simpler one, which they prove first along the way to their main result. Okay, and their simpler result says the following. It says that linear optics with post-selected measurements is enough to do universal quantum computation. Okay, and in fact, it's very the proof of that result is like a very simple trick. So basically, what you do is you use what the people call the dual rail representation. That's this thing here, where you have a whole bunch of photons. Let's say you have n photons and 2 n modes. Okay, and so each photon can just be in one of 2 modes. And if it's in its top mode, then that means that a corresponding qubit is 0. And if it's in its bottom mode, then that means that qubit is 1. Okay, so we're going to use the photons to encode qubits in that way. That's all it means. Okay, and so then the question is, can we simulate a qubit-based quantum circuit, in this way? Okay, well, it's easy to do a 1-qubit gate. A 1-qubit gate, in this representation is just a beam splitter, right? The question is, how do you do a 2-qubit gate? Okay, and in ordinary linear optics, you can't. There's no way to get a universal, 2-qubit gate this way. Okay, but what KLM showed is that if you can do some beam splitters and then you post-select on the outcome of certain measurements, then there may be something that will only happen. There will be some outcome that will only happen with 1/4 probability. Okay, but if it does happen, then you will have implemented a 2-qubit gate, which is a universal one. In fact. Okay, so you do these measurements, you post-select, and then you get if it succeeds, you get a controlled sign gate. Okay, which is this gate here, and which is known to be universal, combined with 1-qubit gates. Okay, so and I think I put on the homework. You can try to figure out for yourself how to do this, right? It's really a matter of messing around with things and then finding a gadget that works for this purpose. Okay, so that was a beautiful result. Okay, but now we can easily extend it further, and we can say as long as you've got post-selection, as long as we're already assuming you've got that power, you might as well, instead of just doing quantum computation, you might as well do post-selected quantum computation. right? Because you've got the post-selection anyway. So we could say that post-selected linear optics actually gives you the full power of post-BQP. Okay, you could say under post-selection, actually linear optics does become as powerful as arbitrary quantum computing. Okay, is one way to phrase their result. Okay, so now let's just finish the argument. Suppose that we had a fast classical algorithm for boson sampling. Okay, then what that would let you do is, because you could run that algorithm, feed it for, to a classical. So that would let you, you could just take that fast classical algorithm, post-select on its outputs, and that would let you do is let you take a post-BQP computation, which you can do with post-selected boson sampling, and it would let you do it in post-BPP, because now you would have a classical simulation. So we would get the consequence that post-selected classical computation would equal post-selected quantum computation. Okay, but now this, now we're cooking with gas. Okay, because we saw that post-BQP, is PP, whereas post-BPP is in the polynomial hierarchy, which means that p to the sharp p would be in BPP to the NP, which is in the hierarchy, which means that pH collapses. Okay. So this was their alternative argument. Right. So now, like I sort of stared at this, and there was something that struck me as strange about this argument, which is that it arrives at exactly the same place that we arrived at, by using the sharp p completeness of the permanent. Okay, and yet, in this argument, we never once had to say that the permanent is sharp p complete. Right? We never once used that fact. Okay, so it was as if the KLM quantum computing proposal somehow knew about the sharp p completeness of the permanent. Right? But if that was true, then one ought to be able to use KLM to just prove the sharp p completeness of the permanent itself in an alternative way. So indeed, that can be done. So this is what I did in a later paper. And it's really just sort of putting together things that we've already seen. So what you could do is just start with some canonical sharp p problem. So let's say you're given a polynomial time algorithm that computes a Boolean function, mapping n-bit inputs to 1s and -1s. Okay, and you would like to compute a sum, which I'll call S, which is just the sum of f of x over all x's. Okay, this problem is sort of clearly sharp p complete, right? Just like by the definition of sharp p, basically. Okay, now it's quite easy to construct a quantum circuit, where some amplitude will be proportional to this S. Okay, how do you do that? Well, here's one way to do it. Okay, so just start with n qubits in the all-zero state, Hadamard them all. Okay, then apply a phase, conditional on f. So like multiply each of your amplitudes by f of x. Then Hadamard all of your qubits again. Then measure in the computational basis. This is actually exactly, the Bremner-Joseph-Shepard kind of computer, the IQP computer. Okay, so this is all you have to do, and then you can calculate what will be the final amplitude of the all-zero state, if you do the circuit. Here, I can give it as an exercise for you, right? It is not hard to work out that the amplitude of the all-zero state will simply be s over 2 to the n. Okay? Basically, it gets a contribution from every value of f. Okay? Okay, but now, we know that using post-selected linear optics, it is possible to simulate any qubit-based quantum circuit, right, using the KLM construction. Okay, so, you create this dual rail thing, simulate your quantum circuit, this one over here, using a network of like post-selected controlled sign gates, and 1 qubit gates, whatever. Okay, and then make a measurement at the end. Ask what is the probability that that we, or with what amplitude, let's say, did we get back to the initial state? Okay, so we can calculate that. So we're applying some optical unitary U here, gets lifted by homomorphism to an n qubit unitary, and we want to know what is this matrix element, right? What's the amplitude that we stay in the state we started in? Okay, and this is just going to be, because we're just simulating the qubit-based quantum circuit, it's just going to be this same thing, this amplitude here, but then with an additional factor of 1 over 4 to the c, where c is the number of controlled sign gates. Okay, because each of our c sign gates only succeeded with a fourth probability. We post-select on it's happening. Okay, now the last thing we need to observe is just that this amplitude here, by the formula that I gave you yesterday, is a permanent, right? It's the permanent of some submatrix, in fact, of our unitary U. Okay, so what we've done is we started with a sharp p-complete problem, and we constructed a matrix, namely this one, whose permanent gives you the answer to the sharp p-complete problem. Therefore, the permanent is sharp p-complete. QED, right? So, if you want that the permanent of a matrix of zeros and ones is sharp p-complete, then you have to do a little bit of more work. But, this certainly gives you that the permanent of a real matrix is sharp p-complete. Okay. Okay. And I think, yeah.
Is there an interesting class where it's like a weakening of post-selection, where you can't post-select on exponentially small probabilities?
But only on polynomially small events?
Like that.
Okay, so the issue is you can consider that, but if you do, you're just going to get standard BQP, right? Because if if your event can only have polynomially small probability, then you might as well just repeat an ordinary quantum computation over and over until the thing happens.
Okay.
And then you could just simulate it that way.
In between.
You could say, okay, whatever, you can post-select on events with probability 1 over n to the log n, right? Or you could have, you could take intermediate stuff between polynomial and exponential. But well, there might be. I can't think of one right now, but there might be.
Okay.
Yeah. Okay. Yeah.
Doesn't you have to require also that C doesn't grow too fast with n?
No, it doesn't matter. It's irrelevant here, right? Because we're just trying to prove right now that the permanent is sharp p-complete, which means the ability to calculate this exactly would let you calculate this exactly. Okay, you know n, you know c, so just divide. You got the answer. Okay, good. So now what I really wanted to talk about is sort of starting to make these results more sort of closer to physical reality. Okay, or more realistic in some sense. Okay, and so now if we try to do this, the most obvious problem is that the entire hardness argument that we gave hinged on the difficulty of estimating a single exponentially small probability. Okay, and now this is an obvious problem, right? Why? Well, for one thing, an experiment is always going to be subject to error, right? The gates will be imperfect, the photon sources will be imperfect, and so on and so on. Okay, so not even the experiment itself can sample exactly from the Boson sampling distribution. Okay, so therefore, it is completely unfair to require, the classical simulation to sample exactly, right? If even the experiment itself is only sampling, at best approximately, from this distribution, then we should also allow classical simulations that would also only, sample from approximately the right distribution, right? That's only fair. Okay, but as soon as we do that, then we find that, the entire, argument that we gave previously falls apart. Okay, now let me explain why. This is important. Okay, the problem is this. Okay, so what should we require? All right, let me define what we want. So I'll define, the more realistic task to aim for, which I'll call approximate boson sampling. Okay, and this is, will still require a quite accurate approximation, but this is sort of like, the absolute sort of least that that we could be asking for, right? Which is given as input your m by m scattering matrix U, your optical your mode mixing unitary. So recall that d sub u will just be the distribution where the probabilities are given by the absolute squares of the permanence of the appropriate submatrices. Okay, so d sub u is like this, is the distribution over outputs obtained by running the boson sampling experiment, with scattering matrix U and with the standard initial state. Okay, now the problem will be to output a sample from some probability distribution D such that the total variation distance between D and D sub U is at most epsilon. Okay, and to do that in time, which is polynomial in m and n, the number of photons, the number of modes, and also in 1 over epsilon. Okay, so this is just, we're like asking for, reasonable scaling with the, with both the size of the experiment and with the desired error. Okay, and now, the total variation distance, if you haven't seen it, it could be defined for physicists as the classical version of the trace distance. Okay, it's, if you had two distributions like this, then their variation distance is just a half times the sum of the absolute values of the differences of the probabilities. Okay, and so this is like the standard sort of physically relevant measure of the distinguishability of two probability distributions. Okay, you can prove that the variation distance tells you exactly how well a sample from the one distribution can be distinguished from a sample from the other by a single shot experiment. Right, and that I also put on the homework, to prove that. Okay, so in particular, variation distance, is nice because it's additive, satisfies the triangle inequality. Okay, which means that if we had like a bunch of gates, or a bunch of beam splitters, let's say, in our optical network, and each one was subject to some small error, in variation distance, then as long as we could control the error in each one, then we could also control the amount of error in our induced by our entire network. Okay, so this seems like a reasonable thing to hope for, and sort of like the bare minimum that we could hope for, right? Like you can't it would be easy to get a result if we just said the probabilities have to be multiplicatively close to the true boson sampling probabilities. Okay, but that's way too much to ask for, right? That's not realistic. Okay, whereas this seems, actually on the verge of realistic.
So that time is to sample one instance?
Yep, that's right. That's correct. Okay, so now, what's the problem? Well, suppose that this is our unit or m by m unitary U, which we get to specify. Okay, now what we're going to do, in order to try to run our argument, is we're going to try to take some n by n matrix, say X, whose permanent we would like to know, and we're going to try to embed it somewhere as a, or some scaled version of it as a submatrix of U. Okay, so let's say, we stick it here. Okay, all right, well, the first thing, we could just try to stick it in the top left corner, let's say, just like we did before. All right, well, what's the problem? Well, we've got to think now of the classical sampling algorithm as an adversary, okay? And, it's an adversary who's trying to solve approximate Boson sampling, thereby satisfying our hypothesis, but doing so without having to estimate a permanent, okay, without having to solve a hard problem. Right, and any way the adversary can think of to do that, it's going to. Okay, so now what will the adversary do? I see this top left submatrix is the one you care about. Fine, I'm never going to output that output. Okay, I'll just never output this this state I. Okay, so I'll still be a good approximate sampler. I'll output all the other stuff with the right probabilities, but I'll just be wrong on this one event that has exponentially small probability anyway. Right, so I'm still, a perfectly good approximate sampler, but I now tell you nothing about the one permanent that you cared about. Okay? All right, so then you think, all right, I can foil this adversary. So you think, all right, I'm going to just take X, but I'm going to smuggle it in at a random place. And I'm not going to tell the adversary where I put it. I'm going to just put it somewhere else. Okay, and so then, but the adversary is clever. Okay, and the adversary sees that, this unit, looks at this unitary, sees that it's filled with like a bunch of more or less uniform kind of, junk, just, bunch of, entries pointing every which way. But then there's this one n by n submatrix that looks a hell of a lot like, it came from starting with some 3-sat instance and then applying variance reduction. And the adversary says, something mighty suspicious here. Hey, why don't I just never output, this, the answer corresponding to that submatrix? Okay, and now again we're screwed. Okay, so the question is, what can we do to foil this adversary? Okay, what can we do to make the adversary solve a hard problem in order to succeed at approximate Boson sampling? All right, so, we thought about this for a while, and I'll tell you the best thing that we came up with. There might well be a better way, but, here's the best thing that we could think to do. Okay, so first thing is, we're going to want to choose our unitary transformation U uniformly at random from the Haar measure. Okay, so just pick it, a completely random unitary. Okay. And now, that's a, sort of a natural thing to do in its own right, right? For example, if you just applied a whole bunch of beam splitters with random angles, okay, then you can show that before too long you're going to converge to this Haar random measure, right? So it's, it's not hard to do. Okay, but what's particularly nice about it is that one can prove the following fact. Okay, so fact is, suppose that n squared is much smaller than m. So we're in this dilute limit, right, where the number of modes is at least quadratically greater, say the number of photons. Okay, so then and the claim is that if you look at a small enough submatrix of U, it is going to be close, say in total variation distance, to a matrix of just independent Gaussian entries. Each one with mean ZRL and with some, suitable variance that you could calculate. Okay, now why is that true? Well, it's intuitively kind of what you'd expect if you think about it a little. Okay, so first look at any one entry of U. Right, it's not hard to see that if you have a Haar random unitary and you look at any one entry of it, it's going to look pretty damn close to Gaussian. Right, not exactly Gaussian because, for example, it can never exceed 1 in absolute value, whereas a Gaussian would have tails that go off to infinity. Okay, but it's, it's really close to Gaussian. Okay, and in fact, if you looked at, let's say, any k entries, in some row, as long as k is much smaller than m, they're going to look like just a whole bunch of independent Gaussians. Okay, now eventually, if k is large enough, this will stop being true. Why? Because you'll start noticing the unitarity of the matrix, right? You'll start noticing that that the norm of any row or any column is 1 exactly, right? Which it wouldn't be for a bunch of independent Gaussians. Okay, but if you look at a small enough subset of entries, then intuitively you're not going to notice that. Okay, and this just says something a little more general, that even if you look at a small submatrix, small enough submatrix, you're still not going to notice the unitarity of the matrix. You'll still just see a bunch of independent Gaussians. So, Alex and I proved this in our paper. The way we proved it was by using math. We, about 5 pages of math. And then, after, we just sort of ground through and we did it. And after we did it, we discovered that there were, similar, and even much better things known in the random matrix theory literature, except that they never actually bound the convergence rate. No one cares about the rate of convergence to the Gaussian distribution, whereas we needed that. And also, they always talk about real orthogonal matrices instead of unitary ones. Okay, but other than that, yes, this is sort of a known fact. Yeah.
Do you think it should relate to the decoupling theorem that we talked about in the last lecture?
Decoupling theorem? Oh, I don't know. That's a good question. I have no idea. So, but yeah, it's saying you look at a small enough set of these events, and and they're going to look more or less independent. Okay. So now we can imagine the following thought experiment. Let's suppose that X is a matrix of IID Gaussian entries. Okay, so each one, complex Gaussians, say with mean 0 and variance 1. Okay, this is, a very nice, very standard random matrix ensemble, right? Okay, and let's say that you've got a matrix that's drawn from that ensemble, and you would, for some reason, you would like to know it's permanent. Okay. Okay. Well, then, here is a strategy by which we may be able to force a Boson sampling algorithm to tell you something, at least indirectly, about that permanent. Namely, we could create an m by m Haar random unitary matrix U, where m is, at least quadratically larger than n. And then we'll, just like before, we'll smuggle in X as a random submatrix. Okay, we'll pick a random set of rows to stick it in. Okay, and then we'll just take this U, hand it off to the sampler. Of course, not telling the sampler where we stuck X. Okay, and now, the sampler is in more trouble. Okay, because the guy stares at this thing, and it just looks like a giant Haar random unitary matrix. Okay, and yes, there's some submatrix that looks, that's an IID Gaussian, but every submatrix of that size looks like an IID Gaussian. Okay, so, even just information theoretically, the adversary has, almost zero information about where, which of these exponentially many submatrices might be, the one that we cared about. Okay, right? It just sort of totally lost in the noise.
You deleted the submatrix?
Yeah. So let's say so here's, okay, more concretely, here's how we could do it. Start with X, and then pick a unitary U uniformly from the Haar measure, but conditioned on it, containing X as this submatrix. or containing epsilon x as this submatrix in this, appropriate place. Okay, and one can show that that can be done efficiently. Okay, yeah, but yeah, that would be one way to do it. Okay, so and the important point is that you'll then get a U that sort of, in some sense, just purely information theoretically leaves almost no trace of which x you started with, right, or of where x was. Okay, so now you feed this U to the adversary, and now again the adversary has to solve the approximate Boson sampling problem. So let's say has to sample from the set of all the different n by n submatrices of this, say, leftmost m by n matrix, right? Each one with with a suitable probability. Okay, now this the Boson sampling algorithm is allowed to make errors, right? It's allowed to be approximate. Okay, that means it is allowed to be wrong about sort of an epsilon fraction of these outputs, right? It can get the probabilities badly wrong for, say, an epsilon fraction of these outcomes, and it can also get the probabilities a little bit wrong for all the remaining outcomes, right? Because it just has to satisfy this variation distance constraint. Okay, but as long as it doesn't know where x is, then it has to be mostly right. It has to be almost right about most of the probabilities. Then with high probability, it's going to be almost right about the squared permanent of x. Okay, and then we still don't know. It will still take exponential time if we run this algorithm over and over until it gives the output corresponding to x. But now we could at least play the same game with BPP to the NP in order to learn within the polynomial hierarchy about the permanent of x, and and thereby get our desired contradiction. Yeah, Patrick.
Yeah, I was just wondering, could the adversary not look at the inner products in the rows and columns of the matrix where you've inserted x to determine where x actually is, because you'll no longer be exactly orthogonal?
Oh, no, you will be exactly orthogonal, because you're going to complete this to an exactly unitary matrix. Okay, good. Yeah?
Do you have any hard proof that there's no technique to find x?
Yes, that part we can prove. Okay? That part, it's really just using the fact that x was close to IID, right? The x we care about has like the same distribution as the submatrices do anyway. So yes, that part we can prove. I'll tell you later about the part that we can't prove. Okay? So, yeah, okay. Yeah.
But then the question is reduced to only x's of that type.
Yes, that's correct.
And that and specifically for that it's also difficult?
That's exactly the question that I'm coming to right now. Okay? So now, yeah. Yeah.
Strategy, you kind of apply that all other matrix elements will be easy for adversary.
Oh, well, they might not be, right? I mean, but if we're doing a reduction, the only thing we can do is to say, well, at the end of the day, we have to start with some problem and get a solution to that problem from this embedding, right? So in some sense, we're using the fact we are indirectly saying that like all of these submatrices are hard in some way, right? Because they all look, more or less the same, okay? But the way that we're formalizing that is by saying we could smuggle in the x that we care about, and you're not, the adversary is not even going to notice it among all the other ones. Okay?
You actually don't know the strategy for adversary.
No, we have no idea. Right, we have no idea what the adversary strategy is. We have to argue, we have to give an argument that works regardless of their strategy. Okay? Okay, so let's let me now sort of define a computational problem, for clarity, which I'll call GPE, or Gaussian permanent estimation. Okay, and this is just the problem that you're given one of these IID Gaussian matrices. And you'd like to estimate, let me say for now, the absolute square of the permanent of x. And you'd like to do so to within a small additive error. And by small, I'll mean plus or minus epsilon times n factorial. Okay, so another homework problem that I gave you is to prove that the expectation of the permanent squared of x is if x is IID Gaussian like that is n factorial. Okay, not surprising. You know, that's just the variance of the permanent, basically. Okay, so this is sort of the natural scale for estimation. Okay, I'm asking you to just get within epsilon of that. And you don't have to do it for every matrix. You only have to do it with probability at least 1 minus delta over the choice of x. Okay, and to do all this, you can use time, which is polynomial in n and 1 over epsilon and 1 over delta. Okay, so that's the problem that's going to be relevant to us. Okay, so now I can state sort of the main theorem that Alex and I prove in our paper. Okay, it says this. Says if we had a fast classical algorithm, polynomial time one, for approximate boson sampling, then we could solve this Gaussian permanent estimation problem in the polynomial hierarchy, you know, in BPP with NP oracle. Okay, so so this is the sort of more or less as far as we're able to get. Okay, now we think that this is already a pretty implausible consequence, right? Why? Because Gaussian permanent estimation, right? You've got a sum of n factorial contributions, right, which are pointing in all different directions. Typically almost all of these random contributions to the permanent are going to cancel each other out, and the thing you're trying to estimate is this tiny little residue which is left over. Right now, we generally don't expect to be able to do that sort of thing, within the polynomial hierarchy, right? At least it would be a surprise if we could. Right, almost as much as if we just had a fast algorithm outright for it. Okay, now I know that may not sound very convincing. Let me make a conjecture to make things more concrete, and then I'll tell you about some evidence for the conjecture. So we may stick our necks out and just conjecture that this GPE problem is already sharp P hard. Okay. Yes, for under randomized reductions. Thank you, Guy. You can just imagine that's written there. Okay, so in other words, we may conjecture that being able to solve this problem, for Gaussian, being able to estimate the permanent for Gaussian matrices will just let us do so for any matrix. Okay, and just let us solve sharp P outright. Okay, now that sounds pretty bold, but I'll discuss later why one might believe that. Now let me give this conjecture a name. Let me call it happy face. Okay, this would make us happy if it were true. Okay, in fact we've offered $1,000 reward for anyone who proves it. Okay, what? Yeah. Where is Feynman's ghost here? Okay, except is it true? It's true. All right, awesome. Unfortunately, to collect the prize, you're going to need a proof. But I'm very happy to know that it's true. Okay, so if conjecture happy face is true, then this would imply that if you had a fast classical approximate Boson sampling algorithm, then that would imply that the polynomial hierarchy would collapse. Okay, so basically conjecture happy face would would essentially rule out even a fast classical algorithm for approximate Boson sampling. Okay, and that this would indeed make us happy. Okay, so now, but this seems like a pretty bold guess. So, why might anyone believe this? Okay, well, and this is where we're going to start for the first time to use sort of the special properties of the permanent, in complexity theory that make it different from just any old sharp P complete problem. Okay. So the permanent has is well known in classical computer science to have an amazing property which is called random self-reducibility. So let me explain what that means. Okay, suppose that instead of talking about the complex numbers, we were talking about a finite field. Okay, so suppose X were just a uniformly random matrix in F to the n times n, where F is some finite field. Okay, so, and suppose that we wanted to know the permanent of X. Okay, and now suppose that we've got, a magic box. Okay, and this box will tell us the permanent of any matrix we feed to it, except only with 80% probability. Okay, it's a sort of it's a discount oracle. Okay, it's 20% of matrices. It's totally wrong, and we have no idea which 20% either. Okay, and now we've got our matrix X, and we would like to know its permanent. Okay, and the question is, can we use this cheapo box to learn it? Okay. What won't work is just to feed in X to the box, because for all we know, X happens to be one of the matrices where it fails. Okay, what we want is that regardless of what X is, that we will succeed in learning its permanent with high probability, regardless of what fraction the box fails on. Yeah.
So it's not random as this for every matrix, but
no.
Specific on the matrix you get correct or wrong outcome.
All we know is that there is some 20% of matrices on which the box is wrong. You have no idea how they were, chosen or what distribution they have. Okay? So, well, it turns out that there is an amazing way to use this discount box to learn the permanent of an arbitrary matrix. Okay? How do you do it? Well, here's how. First thing you're going to do is you're going to pick a random other matrix, Y. Okay, just totally unrelated to X. Okay, you're just going to pick some Y. Okay, and now we're going to consider the permanent of X plus T times Y, where T is a scalar, in the field. Okay, let's call that thing P of T. All right. Now, I claim that P of T is actually a low-degree polynomial in T. Okay, why? Well, just look at it, right? Each of the entries of X plus Ty is an affine function of T. You take the permanent, you're just multiplying n of those things and then adding up a bunch of them. So you get a degree n polynomial in T. Okay, but furthermore, I claim that except when T equals 0, each of these matrices, is essentially a random matrix. Okay, why? It's the same reason why the one-time pad is a secure cryptographic code, if you've ever seen that. Right? You can take any message whatsoever and just, add to it, like bitwise exclusive OR it with random garbage, and the output will be indistinguishable from random garbage. Right? Same thing here. Okay, you take any matrix X and you add a random matrix to it, you get a random matrix. And a random matrix times a non-zero scalar, over a finite field is again a random matrix. Okay, so all these things are random matrices, which means that, if we feed into our oracle, x plus y, x plus 2y, x plus 3y, and so forth, then we know that with high probability our oracle is going to be right on maybe 80% of these. Okay, regardless of what fraction, it doesn't matter which fraction it's wrong on, right? Because these things are random. Okay, so now we've got, there's this degree n polynomial in a single parameter, and we know its values, let's say like 80% of points. Okay, but now we're just doing low degree, noisy polynomial interpolation. This is something that we know how to do, since the 1960s. Something called the Berlekamp-Welch algorithm, right? That given a bunch of values of a polynomial, some of which are noisy, lets you reconstruct the polynomial. Once you've reconstructed it, then you just have to evaluate it at 0, and that gives you the permanent of your matrix. Yeah? Question? Yeah.
Just a technical one.
Yeah.
Is x plus dy done on the field or is it done on the real?
Done on the field. It's done on the field. Okay. So, in fact, you could, your box could even work for only a 1% of matrices. Okay, and this would still work. Okay, amazingly, as long as the field is large enough. Okay.
Why did you need the order to be finite?
Oh, well, because we wanted to be able to have uniform random sampling from the, yeah.
But do you need the order to be large compared to n?
You do, yeah, you do. That's a good point. Yep. Yeah. Yeah. Okay. So in fact, at least over finite fields, the permanent does have exactly the property that we want. Okay, it has the property that computing it, even just on a small fraction of matrices, is already a sharp p-hard problem. Okay, so in some sense, we merely need the same thing to be true over complex numbers as known to be true over finite fields. In some sense, this is what we're asking for. Okay, now in particular, here's what we can prove. By adapting these ideas, we're able to prove that exactly computing, say, power of x squared, for most Gaussian matrices X is indeed a sharp p-hard problem. Okay. So using polynomial interpolation methods, we can prove this. In fact, we're even getting like an exponentially good approximation to the squared permanent for most Gaussian matrices is a sharp p-hard problem. Now, of course, we also know, I showed this to you yesterday, that approximating the permanent or squared permanent for all matrices X is a sharp p-hard problem. Okay, so to prove the Smiley conjecture, we would merely need to sort of combine these two things. Okay, get the approximation and the average case, together in the same theorem. Okay, approximation is sharp p-hard. Getting it the exact answer for most matrices is sharp p-hard. Okay, we want that approximating permanent for most matrices is still sharp p-hard. If it is, then we're done. Okay, so that's I think it's a nice question, even just for classical complexity theory, even if you didn't care about boson sampling at all. Say that if you're interested in trying to prove the Smiley conjecture, then probably the first step to proving it would just be to understand the anti-concentration properties. So just understand the statistical properties of the permanent of a Gaussian matrix. Okay, that seems like a prerequisite. And so in our paper, we also study that question. And we have a second conjecture, which we call the permanent anti-concentration conjecture, the PAC. And this one says that if you take an IID Gaussian matrix and you look at, say, the absolute value of its permanent, then there is some polynomial p such that the thing is going to be like a lot smaller than square root of n factorial, only with a small probability. So it's going to be less than root of n factorial over p of n over delta with probability at most delta. Okay, so what we need is that if you look at like the density function of a random permanent, that it doesn't look like this, where it's sort of almost entirely concentrated on like really small values with just a tiny, like this little tail that goes out further. Now, I should say that, by physics standards, we know that this conjecture is true because we tried it out and we tested it in MATLAB, okay? We know that the distribution looks nothing like this. It looks, yeah, it's a little concentrated, but maybe it looks like this, but it's, nowhere near bad enough for, for this, okay? So, now, another thing that we can prove is that if this anti-concentration bound is true, then computing the permanent of a Gaussian random matrix is of the same difficulty as computing the absolute square of the permanent. Okay, which you would hope, but and indeed it is true, assuming that the permanent has reasonable statistical properties, which again we know via MATLAB that it does have. Okay, so we are able to prove the analog of this conjecture with a determinant in place of the permanent. Okay, again, the determinant has geometric structure that makes it much easier to understand. We were able to do that. For the permanent, this is connected to actually to known open problems in probability theory, and in fact, the best current result in the direction of this conjecture is from a few years ago by Terry Tao and Van Vu, and it's not strong enough for us. So, I've consulted with Terry Tao about it. He says that he could maybe get sort of close to this, but new ideas are going to be needed to get to this. Okay, and this again I think seems like it should be a prerequisite for proving this conjecture. So at least we know something about why even if true this would be difficult to prove. All right, so I would now like to move on and talk about my last topic, which is implementation of boson sampling. So, you can view this as a complexity idea, but of course, this boson sampling sort of immediately, suggests a class of physics experiments. Okay, where what would you do? You would generate a bunch of identical single photons in Fock states, send them into an interferometer, so a network of beam splitters and phase shifters. Blah, 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 blah. Okay. And then you would have an array of photodetectors that measured where the photons ended up. Ideally, I should say these would be what are called number-resolving detectors, meaning that they would just tell you how many photons arrive in each port. If they're not number-resolving, if they're just bucket detectors, so they just tell you whether there's 0 photons or there's more than 0, that's still okay for us as long as you've got enough modes. Okay, if you have enough modes, then we proved that you can ensure that, like with high probability, there's not going to be any photon bunching anyway, at least if you have a Haar random unitary. Okay, and so then, you could just detect 0 photons versus 1 photon. Okay, anyway, you would then, you would make this measurement, and then what would you be testing for? Well, basically, you'd be testing, do the statistics of the outputs agree with the prediction of quantum mechanics? Okay, so are the outputs, is the probability of output S does it indeed look like the permanent of the appropriate submatrix of your scattering unitary, with the scaling factor? Okay, so so you'd be looking for peaks and troughs in your probability distribution that looked like these permanents. Okay, now this this sort of experiment, some of you may know, was done about a year ago. There were actually 4 groups that independently published experiments in it. Well, one in Rome, one in Oxford, one in Vienna, and one in Brisbane. And so they did this experiment with 3 or 4 photons. Got to start somewhere. And with 5 or 6 modes. Okay, and the result was that they confirmed to within experimental precision that the amplitudes for 3 photon processes are indeed given by permanents of 3 by 3 matrices, and likewise for 4 photon processes. Okay, so within 10% error or whatever. Okay, but you indeed see the bumps that sort of going the right way. So what should the goal be here? So what we think is that the goal should be to try to do this sort of experiment, if possible, with be 20 photons or 30 photons or 40, something like that, and with a suitably larger number of modes. Okay. So why do we, what is special about these numbers? Well, nothing too magical, but what would be nice would be to do an experiment where the experiment itself is actually sampling from the Boson sampling distribution faster than our fastest fastest known simulation methods running on a classical computer could do so. Okay, and the fastest known simulation methods are going to require time that scales exponentially with n. If you use this Glynn formula for the permanent, it's something like this. It may even be more than this, but more than this, I'm not willing to say. Right? This seems like a pretty hard lower bound. Classically, at least with any known method. And of course, if our complexity conjectures are true, then, at least asymptotically, you shouldn't be able to do much better than this. Okay, so then, you can try to estimate, okay, at what point, is the experiment doing the thing with less effort than the classical simulation is. Now, this is inherently a fuzzy question, right? Because it's like, how do you with what computer are you using? How do you measure the amount of time needed to do the experiment? Like, do you count graduate student labor hours? Do you count, what exactly do you count? Okay, but it seems like, the crossover point would be, roughly somewhere in this range. And so that's, seems like a thing to aim for. Okay. What error rate? Yeah, that's a good question. Small error rate. So what we would really like is just for the errors to be small enough that you can actually see that the fluctuations point in the right direction of the permanent of the matrix. Okay, that's really what we're looking for you to be able to see a signal that makes a direct connection to the permanent of the matrix.
But you would expect the one norm deviation to grow with the size of the inner parameter.
The one norm deviation? What do you mean?
Yeah, but
yeah. You mean the amount of error?
Yeah, I mean,
yeah.
If you have some error per element of the circuit, then the error is going to grow with the.
Yes, that's true. Right. So okay. So there's now a question. Let me now come to this question. Without further ado, which is, is there any chance that you could scale to this sort of size, without, say, needing the whole machinery of quantum error correction? Which, of course, if you had all of that machinery, then at that point, presumably you might as well just build a universal quantum computer, right, and be done with it. Okay. Okay. Well, what's working for us is that the optical elements themselves, the beam splitters, the phase shifters, are extremely reliable, right? They have extremely low loss. Okay. The detectors, are not perfect, but they've been getting better. So NIST now has the detectors that can have something like 98% efficiency, I think, depending on I can tell you what the biggest issue is. The biggest issue that's emerged in trying to scale this up is the photon sources. Okay, so as some of you may have heard, there does not currently exist on Earth a reliable deterministic single photon source. Okay, so what we have is, we have sources that, will, output a photon when they feel like it. Okay, so, yes, the one photon will eventually come out, but, you don't know exactly when. Okay, it will, it may take its time with it. Okay, and so what can you do with that kind of source? Well, if you had, a whole bunch of these sources, you could wait for all n of them to happen to output a photon at the same time. So then you would see the n photon interference pattern. Okay, the problem with that, and that is indeed what was done in the experiments that were, that were done so far, right? That's what's done in many, many quantum optics experiments. Okay, the problem with this is obvious. Problem is, the amount of time that you're going to have to wait until all n detectors happen to shoot out a photon at the same time is going to grow exponentially with n. Right, so then, you're not going to get any scalable speed up in this way. Okay, so then the question is, we could just wait for reliable single photon sources, to be invented, right? There's nothing in, fundamental physics that rules them out, certainly, right? And there are even ideas on the table, something called optical multiplexing, for how you might be able to get them. Okay, so one could just try to wait for that. Okay, but now we could also look at what are the sources that exist today. Could they be good enough? Okay, so
Is there no way to make a photon wait for the other photon before you?
Well, that's actually what this optical multiplexing idea is basically trying to do that. It's basically trying to use logic to, using some optical logical gates to sort of get the photons to route themselves so that they all show up at once. Yeah. That's, so that's an idea on the drawing board. No one has really done it yet. Okay, so what's certainly, easy to produce, a kind of source that we do have in spades, is a source that produces coherent states. Okay, a coherent state is just a particular type of superposition of 0 photons, 1 photon, 2 photons, and so forth, right, where the number falls off by a Boson distribution. Okay, coherent state is the output of a laser, for example. Okay, so, these are very, very plentiful. Unfortunately, these are completely useless for boson sampling. Okay, why? Well, because some of you may know this basic fact that if you have just a whole bunch of coherent states as your inputs and you apply a linear optical unitary to it, then the output is going to be another product of coherent states. And how will the final states be related to the initial ones? They'll be related by a matrix vector multiplication. Okay, so in other words, if your inputs are coherent states, then your whole experiment is trivial to simulate with a classical computer. Okay, so, or to put it another way, right, coherent states basically just behave like classical light waves would.
But you're doing single photon detection. That's
yeah, but that still doesn't matter, right? Because you've got a product of coherent states, and so each measurement, right, you could calculate the distribution separately for each one on the output probabilities, and it has no effect on the other ones. Yeah. So the fact that we've got single photon detection still doesn't help us here. Okay, but there is hope. Okay, because there's that there is another thing that is widely available today, and which has been really the workhorse of a huge number of quantum optics experiments for the last 20 years or so, and this is called spontaneous parametric down conversion, SPDC. Okay, unlike most of the acronyms in these talks, you can't hold me, to fault for this one. Okay, so what is SPDC? An SPDC source is something that produces, so it's a crystal that you sort of stimulate with a laser, and then sometimes it will output an entangled state, and the entangled state will look like this. So where I is a number of photons. Okay, so superposition over no photons, 1 photon this way, 1 that way, 2 this way, 2 that way, 3 this way, 3 that way, and so forth. Okay, now what you can do with an SPDC source is you can monitor one of the outputs and see when you get 1 photon here. And anytime you see 1 photon here, you know that there was 1 photon there also. Okay, so this gives you what's called a non-deterministic single photon source, right? You don't know exactly when 1 photon will come out, but when it does come out, it's heralded, okay, as they say. So, so you have, there's another photon you could measure that tells you, that yes, 1 photon did come here. Okay, so yeah.
Wouldn't the fact that they are entangled somehow make the photons that you actually use distinguishable?
So you're remember that you're measuring one of them. Okay, so you're projecting one of, I mean, first of all, it doesn't matter if you do or you don't, right? But I mean, we're conditioning on getting 1 photon, and this left one. Conditioned on that, we simply have a single photon Fock state over here, not entangled with anything. Okay.
But some of them may be 2 and some may be 1.
That's right, but we're conditioning on getting 1 over here. Okay.
If you do that for all of them, doesn't the exponential come back?
Yes, it does. Okay, but now we're going to think a little bit harder, okay? So first thing we can observe is that the exact, the hardness result for exact boson sampling goes through perfectly fine if our sources are SPDCs instead of single photons. Okay, why? Well, because the whole hardness result for exact boson sampling was based on post-selection anyway. Okay, so as long as we're doing all this post-selection, we might as well just have a whole bunch of SPDC sources and then just post-select on the left arm of each one producing 1 photon. Okay, and if we do that, then we simply reduce to the original case of single photon Fock inputs over here. Okay, and and then so we still get that there's one particular event whose probability gives us the permanent of a matrix that we care about. Okay, but of course this is not really what we're after. What we really want is for the approximate boson sampling to be hard, even with SPDC inputs. Okay, so Alex and I sort of kicked this around for years. We didn't really know what to do with this problem. We gave it out to other people. And then just only a few months ago, I was visiting Oxford, and I talked to the experimental boson sampling group there. So it's a group of students and postdocs of Ian Walmsley, and they had an idea which was really striking and which just completely solves this. And then later I found that there were other experimental groups who had independently had the same idea, and we were just kicking ourselves for but it's all for the good. Okay, so let me tell you the idea. I at least decided to give the idea a name. The name that I've given it is scattershot boson sampling, or scattershot BS. Okay, so and this lends itself to many jokes. Like someone pointed out to me that scattershot BS is an excellent way to get a paper in Science or Nature. So. Okay, so what's the idea here? We have a whole bunch of these SPDC sources. And let's say we attenuate each one of them so that each one, let's say that there's n squared of these, and each one has alpha 1 Alpha 1 squared is like 1 over n. So each one has a 1 over n chance of producing a photon in any given run. Okay, so on average, about n of these are going to produce photons. Okay, now we have no idea in advance which of our sources are going to happen to produce a photon. Okay, but we will know after the fact which ones did, because they're heralded, right? So it'll be like ding, ding, ding. This one did, this one did, this one did, right? Now, whichever ones did, we're then just going to run with that. Okay, we're going to just define that to be our input, and now we're going to so suppose that our m by m scattering matrix U was some Haar random unitary matrix, then now, okay, instead, we're still going to be looking at some n by n submatrix of U, right? Except now, this will no longer necessarily be, on the leftmost, n columns, right? It'll both, we won't be able to predict in advance either the rows or the columns of the submatrix, okay? But the probability with which each submatrix is observed will still scale like the squared permanent of that submatrix. Okay, and so, and all of these submatrices, they're all IID Gaussian, so they're all perfectly good for us, right? So, why not use them, right? So, in particular, we can easily prove, under exactly the same assumptions that, under which we showed that approximate boson sampling is classically hard, that approximate scattershot boson sampling is also hard under the same assumptions, like that Gaussian permanent estimation is not in BPP to the NP, right? So you don't even have to make a new hardness assumption here. Okay, so you're still going to be limited by the efficiency of the detectors, but I think that this should already let you do, let's say 10 photons at least with current technology, I would guess. Okay, and hopefully. So this is you could say it's a cautionary lesson about saying that this can obviously never scale, right? It's like yes, but think about it more, right? And you might be able to do it. So I had one. Okay, I promised some people that I was going to say something about this paper by Izard et al. So I'll tell you, let me just say something about that, and then I'll take questions. Okay, it'll just take me 2 minutes. Okay, so so an obvious question is, how do you verify the output of a device? Okay, and so now in our original paper, what we said is that try doing boson sampling with 30 photons, maybe 40 photons, but don't even bother to try to do it with 100 photons or 1,000 photons. Okay, why not? First of all, because you probably can't. Okay, but secondly, because even if you could, how would a classical computer ever verify the answer? Right? You would have to calculate permanence of 100 by 100 matrices, right? And this is just infeasible. So, or we think it is. So, it's not like factoring where you have a fast classical verification method, right? Here we don't know of one. Okay, so, but, on the other hand, there is this sweet spot that one could aim for of 30 or 40 photons, where yes, a classical computer can check the answer, but on the other hand, it would be slower than the experiment itself, right? So that really seemed to us to be the range to aim for. Okay, so then, just this summer, Jens Izard and Gogolin and 2 others put out a paper on the archive, some of you may have seen, where they said that basically, boson sampling is impossible to verify the outputs, so it's useless for testing the extended Church-Turing thesis. Okay, and so the first thing they did is they just repeated this point that we had made ourselves in the paper about that you can't do it with large numbers of photons. They did it like as if we had never said it, but but whatever. And then the second and they didn't even talk at all about why not just do it with 30 or 40, right? So but then the second thing is that they said that the output of a boson sampling device is in some sense completely indistinguishable from uniform randomness. Now how did they get to that conclusion? Well, they had to sort of restrict the verification algorithm so that it wouldn't know the actual labels of the modes. Okay, this is what they did. They proved that for such a verifier, it would take exponential time to distinguish the output of a Boson sampling device from the uniform distribution. Now, to me, the response is pretty simple. Why on earth are you restricting the verifier in this way? It would be exactly like saying, with Shor's factoring algorithm, suppose you had a verifier that could only look at the number of the number of times each digit occurred in the output. So you knew that so many 2s occurred, so many 3s occurred, and so forth. Then such a verifier would have no idea whether Shor's algorithm had correctly factored the number or not. Okay, that's correct, but it's like totally irrelevant, right? Okay, but so we were planning just like a 2-paragraph paper that just explained by these points, and to just respond to them, but then it turned into a 40-page paper because then we decided to just think some more about, okay, what can we actually say about this question of suppose that you did want to do boson sampling with 1,000 photons, is there anything you could do in order to try to verify the output? That's sort of an interesting question. So we were able to say that you can do something. Particular, first of all, we were able to sort of refute basically their claim that the output is just like uniform randomness. Okay, so at a heuristic level, sort of we knew perfectly well that if you take a Haar random unitary U, then the boson sampling distribution d sub u is going to have a good, it's not going to look anything like the uniform distribution. Okay, why? Because there will be fluctuations, right? Each probability in this distribution is the permanent, is a squared permanent of some submatrix. Okay, but these permanents fluctuate. Some of them are really close to 0, some are not so close, right? Each one is a sum of a whole bunch of positive and negative terms. So, of course, they don't perfectly cancel, and you have fluctuations left over. Okay, so we knew numerically that this distribution is nowhere close to uniform. Now we can actually prove that as a theorem. We can prove that with high probability over U, this boson sampling distribution has variation distance at least 0.313 from the uniform distribution. Okay, probably the answer is that it's close to 1, but this is what we can prove. Okay, but then we were even able to go further than that and say you can even distinguish the output of a boson sampling distribution from the uniform from a uniform noise via a polynomial time classical test. Okay, and you can do that despite not being able to calculate the permanent. Okay, how do you do that? You just need something that's a little bit correlated with the permanent. Okay, but which is easy to compute. So you just need to find such a thing. All right, so here is such a thing. Okay, let X be the n by n submatrix corresponding to an observed output. Okay, then compute this thing. Product over all rows of sum over all columns of the squared entry of X. Okay, this is what we call the row norm estimator. Okay, it's just the product of the squares of the norms of the rows. Okay, now we can, this thing is obviously computable in, polynomial time given X. Okay, and we can prove that, well, it's kind of a crappy estimator for the permanent, but it is non-trivially correlated with it. It's a little correlated, and that by itself is perfectly enough to distinguish the output of boson sampling from the uniform distribution, just given a constant number of samples, constant amount of experimental data. Okay? So, this shows a general lesson, which is that there might not be any way to prove definitively that, that your output is boson sampling, and nothing else. Okay, but as soon as you specify your null hypothesis, you say, look, what I'm worried about is that the output is uniform. Or you say, what I'm worried about is that the output is just classical distinguishable particles. Okay, then, for that case also, right, we think that, we can design an efficient test that distinguishes the boson sampling distribution from that null hypothesis. Right, for the classical distinguishable particles, we have a test that we believe works, although we haven't proved it yet. Okay, so In other words, we're stuck doing science, right? It's not a question of mathematical proof, but, we can get pretty good, evidence. Okay, likewise, people constantly raise the objection, oh, but, how could any of these experiments ever tell you about the extended Church-Turing thesis? Because, that's an asymptotic claim, right? It's a claim about all values of n, but, you can only ever do a finite number of experiments. So our response is, well, that's true. Now, would you raise a similar objection to any other scientific hypothesis? Would you say, well, you can never, have any idea if general relativity is true because you only ever test it on a finite number of cases, but there's an infinite number of possible initial conditions, right? The point is this is not a standard that we ever hold ourselves to in science. So, why should we do that here? Okay, the point is if you could do this with 30 photons, with 40 photons, then I think, the extended Church-Turing thesis, becomes a lot less tenable. So that's sort of what we're aiming for. So I'll stop here. Thanks.